We're very happy to have Nushu talk about the RHIC beam energy scan. He's been associated with the RHIC program for a long time, and he's an expert, especially in this beam energy scan program. And he's also written the motivations for why we want to do this, and we'll surely learn a lot from his talk. Just for administrative purposes, I'll just say that if you have any questions, please write them down in the chat box. If there's a very urgent question, which is very short, then you can we can try to take it during the talk, but otherwise we'll have all the questions at the end, and there's plenty of time for discussions at the end. So with that, I'll give the floor to Nu. Please go ahead.
Thank you very much. Good morning, good afternoon, or good day, wherever you are. So I would like to thank the organizers for the kind invitation, and also thank you for participating in this discussion. So I will focus on the recent result from RHIC beam energy scan program. So I will start with outline. After a brief introduction, I will move on to recent result, focusing on three quickly points: collectivity, the collective motion created in high energy collisions; criticality, perhaps we can look for a critical behavior in a nuclear phase diagram. Then I will discuss very briefly about hypernuclei production. This is a new feature at high baryon density. I think it's very important for future of high energy collisions and astronuclear physics. So I would like to mention that. So at the end, I will discuss a little bit future physics and high baryon density, especially focus on the compressed baryonic matter experiment at a fair. If you have questions, feel free to ask, and I have no problem with that. So let me show this slide to discuss basically the definition, the phase, what is a phase diagram. So phase diagram is like, to me, it's like a map for a given degree of freedom, how matter organize or reorganize itself under external conditions. We're all familiar with the phase diagram of water. It is expressed in the pressure as function of temperature. There are many actually phases in the water phase diagram, and you could the big ones, three major ones, are solid state, solid phase, and gaseous phase, and the liquid phase. Depends on what temperature and what pressure you are setting there. There's also a critical point here. So for this talk, what we are talking about is a strong interaction phase structure. This is also not new. If you look at Fermi's note on thermodynamics and statistics in 1953, he already presented a hand-draw phase diagram. Here's the temperature, and here is basically matter density. You can see he was imagining there's such things. This was proposed in 1953, so it's already like 70 years ago. 50 years later, in 1983, when US was preparing for RHIC, Gordon Bain and showed his hand-drawing phase diagram. And here is the temperature, again, same here. And here is the nuclear matter density or baryon density. This was the first time, as far as I know, he drew a boundary, phase boundary between let's call that a normal nuclear matter and then deconfined quarks and gluons. Now we call this part is quark-gluon plasma. As you can see that he put a huge range in terms of what would be the temperature and also density. Temperature is around 200 MeV, and the density here he put on 5 to 10 times of saturation density, which is the ground state of nuclear matter somewhere here. So, so this is a long, outstanding problem. Just because many of us are students here, why this is important. So in physics, whatever physics you do, normally there are two key questions. One is you ask, what is the participating degrees of freedom? Once degrees of freedom is fixed, the next question is what is the structure of matter with that degrees of freedom? Like this case, electromagnetic interaction here. This is about water's phase diagram. So here we ask, what is the strong interacting matter phase structure? So now on the left, I show the state of art phase diagram. This is provided by lattice gauge theory group here. So at a 0 quark mass, this is temperature, this is baryon chemical potential. We have TC and also tri-critical point. And at a finite quark masses, which 0 mass meaning chiral limit, and the final mass we have a critical point showing here. So the pseudo critical point showing here, lattice provide a really precise measurement that is 156.5 plus minus 0.5 MeV. This is well defined. Another important, I think, things we should remember is on a similar calculation by lattice calculations, they predict if this critical point exists, there must be mu B must be 3 times of TC, larger than TC. But this is their calculations. Experimentally, how to determine this critical point still is driven by experimental program. That's why we are trying to use heavy ion collisions to look for this critical point. That's also the beginning of the beam energy scan, the motivated beam energy scan, why we want to do it. So now I just move one step ahead to show you experimentally how do we do beam energy scan. So this is again the temperature, and this is baryon chemical potential. As we know, actually, at a mu B equal to 0, or on the other hand, in very high energy collisions where baryon particles are produced in pairs, so the mu B equal to 0, net baryon density equal to 0. So this is a smooth crossover, as the lattice predict already. And this is a temperature 156 MeV. This property not only predict by the lattice QCD calculation, and also experimentally through jet quenching, through heavy flavor RIA and collective measurement, and also high moment of net proton distributions, we determine this feature. I will discuss some of this in a talk. What we also know from model calculations or model speculations, in higher baryon density and the low temperature region, this transition is a first order transition. If this first order transition is true, and the smooth over at mu B equal to 0 is also true, purely thermodynamically, there must be end point of this is the first order phase boundary. This is a critical point we are looking for. So in order to search for this, we have to change the collision energy. High energy, the higher the energy, the lower the mu B. So RHIC, in order to search for the critical point, we actually lower the beam energy, scanning this way. Eventually, collider mode doesn't work, so RHIC can change into the fixed target mode, extend the mu B to much larger region. So I hope you take away the messages here is we know at mu B equal to 0 the property of the phase structure there quite well, but we do not have enough information yet at high baryon density or lower temperature region, and we don't have experimental evidence so far regarding the critical point. So that's what we are trying to do. So at RHIC, we do this with this beautiful star detector. I'm sure many of you are familiar with it. And this is a typical collider experiment detector. In the heart of this is the heavy flavor tracker. This is for measuring basically charm quark hadrons in collisions at RHIC. Outside the HFT is a time projection chamber showing here. So this part. And outside the inner, there's an outer TPC and inner TPCs. The outside the TPC is a time of flight. TPC and time of flight is for particle identification and momentum determination. I have to say this detector is really one of the best, if not the best, the collider experiment. It provides excellent particle identification and uniform efficiency. This is very important for correlation, especially high order correlation measurement. It's very important. I think this advantage or this has not been surpassed yet. Other collider experiment has to show if they want to show. So the problem, not the problem, the feature of this detector is the rate capability is not as good as other detectors. So this has a modest rate capability. So this is a star detector. In order to prepare for this beam managed scan, STAR actually undertook 3 major upgrades in order to for the beam managed scan program. First, as I mentioned already, the inner TPC is upgraded, already completed in 2019. Then add the end cap time of flight detector array, and this array actually is borrowed from CBM experiment. This is already constructed, but since CBM is not in operation, so borrowed to STAR, and it's also completed in 2019. In addition, in order to improve event plan resolution, STAR also installed a new event plan detector in 2018. All 3 upgrades are very successful. The functionality is enlarged rapidity acceptance, that is from inner TPC part, and extend the ETA coverage, and also improve the low PT coverage and the momentum DDX resolution. Actually, it's actually very beautiful success program. So from this plot, you can see this is rapidity distribution. After the upgrade, you can see the rapidity coverage is extended. The DDX resolution is also improved. The lower, the better. That is a dark black line shows here. The end cap time of flight detector was also very successful. You can see clearly particle identification for KP and the deuterons. The event plan resolution also increased dramatically. What I'm showing here is, I think it's a second order event plan resolution. This is before we use the beam counters, and after with this new event plan detector, you can increase about 20%, which is actually very large number in terms of improvement for the event plan determination. As I mentioned before, this detector is very good for particle identifications. Here is a demonstration of that. So this is TPC, and this is the time of flight. TPC covers from 0.4 to 0.8 GeV particle identification clearly. Then from 0.8 to 2 GeV, we have to use time of flight to select protons. So this is in this region from plus minus half unit and 0.4 to 2 GeV is our, I would call, sweet spot for physics analysis in STAR experiment. TPC efficiency overall is about 80%, and time of flight coverage is about 60%. So overall efficiency roughly is about 0.5. Some regions a little bit better, some regions a little bit worse. So this is the overall situation in terms of particle identification. So In addition, we also have a very good capability to do using topology to reconstruct particles. Here's an example for 5-meson identification. Well, this is a lambda cascade baryons, very well identified. In addition, recently in the 3 GeV collisions, we also identified hypertriton, hyperhydrogen-4, and also hyperhelium-4 also identified. Those are hypernuclei. In the high baryon density region, actually, this is at 3 GeV, there's a huge advantage to study hypernuclei production. So that's actually was kind of surprise, at least to me. We did not know this before. We should have known before, but we did not before. So before I move on to measurement, I want to say one more thing is for the STAR fixed target program. So this is a STAR detector. Normally, we take data in a collider mode. So collision point is around the center of the TPC. The STAR experimentalists are very clever. So they proposed to put a target at the entrance, one side of entrance of the TPC. Then if you have beam shoot on target, you can measure as a fixed target experiment. So why this is important? In the collider mode, we took energy, lowest energy 7.7 GeV. That corresponding to chemical potential 420 MeV for central collisions. With this fixed target experiment, we can extend the center of mass energy to 3 GeV. That mu B is about 760 MeV. Basically, it's a big jump in terms of mu B coverage for the STAR in a really much leading forward direction. So this allows us to do strangeness production, hypernuclei, and fluctuations at high baryon density region. Nowadays, we took lots of data for that. So this is a list, not a shopping list. This is a list what we have. It's a treasure. It's the highest data set in the world from heavy ion collisions in this energy region. On this side is collider running data from 200 GeV down to 7.7 GeV, and this is typical mu B. On the right-hand side, I show you the fixed target experiment. Let me emphasize, especially important is the 3 GeV. We took more than 2 billion events. The 260 million events already processed. We published many papers, but 2 billion events are still in a production mode. So in any case, this is the most precise data in order to map for the QCD phase diagram. It covers energy from center of mass energy from 3 GeV to 200 GeV and mu B from 760 to 25 MeV. So this is very wide range coverage. Now let me move on to some selected result, if there's no question. So I'll start with collectivity. Collectivity, I hope you understand what does it mean. It's just we study some collective motion of for particle productions. Give you one example. If you take a train from city 1 to city B, the train moves together. Although inside the train you can move around, but from looking from distance, the train move in the same velocity. So this is looking for similar velocity or velocities is the way to look at the collectivity. Experimentally, what we do is we expand the transverse momentum distributions by this Fourier expansion. Looking at this each coefficient, you can call that a kind of velocities. You can extract the information. For example, V1 is called directed flow. V2 is elliptic flow. There's also triangle flow and so on. So this is very important because this coefficient can be well evaluated in hydrodynamic calculations. By doing this, we can extract important physics program. Here I show you one, again, use this cartoon to show about anisotropy parameter 2, V2, so elliptic flow. In non-central collisions, the overlap region is ellipsoid in configuration space. In this case, you can see the long axis is Y, short axis is X. Due to interactions, or very violent interactions, this coordinate space anisotropy is converted into momentum space anisotropy. Okay, because this the pressure gradient, the short axis actually becomes longer in the momentum space. In the momentum space, this is because the pressure gradient is much larger in the short axis, and vice versa. How strong, how quick such a transition from coordinate space to momentum space depends on the degrees of freedom and the equation of state. Therefore, by studying these distributions, we can extract this information, understand the matter properties. That's why this has been used extensively in high-energy nuclear collision since 2000. I show you a few nice pictures from STAR measurement. This is one of, I think, very important V2 measurement in STAR experiment. On the left, I plot V2 as function of pions and protons as function of transverse momentum. As you can see in the low transverse momentum region, the light particles, here is pion, V2 is larger than heavy particles, here is protons. On the other hand, in the intermediate PT region, this ordering is reversed. If we use the called the V2 scaling model curve to describe, to fit this, you can see this black dot line and a blue dashed line to describe these distributions. You can see they very well follow such distributions. So this means that the light quarks, ion protons only contain light quarks, they follow the number of quark scaling. In this plot is already clearly shown. On the right plot, I show you the phi meson has 2 s quarks and omega baryons has 3 s quarks. You can see for s quark, they also follow this scaling very well. What does this mean? This means in such collision, gold-on-gold collisions at 200 GeV, s quark, UD quark all experience the collectivity. They move together. All these quarks, like in a train, they're moving together. So that means we have the platonic collectivity, which is a necessary condition for the formation of quark-gluon plasma. That's why this is one of the most important measurements at RHIC. Now, people would ask, we measure the light quarks, what happened to charm quark, heavy flavor? Charm quark hadrons. We did a measurement. We did it with actually heavy flavor tracker, as I mentioned earlier. Heavy flavor tracker gives us a very good pointing resolution. So we can identify charmed quark baryons, those charmed quark particles. Here's the D meson clearly. So you can see this is V2, or number of quarks scaled V2 as function of transverse momentum, and they scaled very well. This scaling meaning that charm quark also experienced the collective motion, just like light quark and S quarks. So because charm quark is so heavy, much heavier than the temperature reached in such a system, that means the charm quark must suffer lots of interactions. This interaction naturally leads to local thermalization in such collisions. So charm quark here helped us to confirm the system reached the thermal equilibrium. That's the important, one of the important measurement, or very important measurement, determine the nature of such collisions. So those are the collective measurements. I want to show you how to interpret the property of the medium. I hope you can follow this. So in order to check the equation of state, we actually sometimes measure, use the property of medium that using the eta over S. Eta is the shear viscosity, S is the entropy. So this is just to form to scale easily. So we multiply by 4 pi. So here's 1. On the right, if we focus on the right-hand side, the result, this is only from 200 GeV collisions. By fitting, using the model, by fitting to the measured V2 and the jet RAA measurement, one could extract eta OS property for gold on gold collisions at 200 GeV. As you can see, this is the model fits result as function of temperature at the TC. So this is reaching unit 1. That means the transition. This is at the transition point. And to the high temperature part, it's increased as function of basically the viscosity increased. So this is for 200 GeV collisions. Recently, there's a publication, the third one showing here. They also fit to the STAR published the result, beam energy scan result, starting from 200 GeV, is the first point, all the way to 7.7 GeV, last point. For each point, they also extracted the eta over S. This is showing here. What I did was I just put these two together, as you can see, that in case of a QGP phase, which I'm showing is here, that's reach the quantum limit. For three energies here, 200 GeV all the way down to 39 GeV, they're all consistent with 1. Oh, sorry, I forgot to mention that here I normalize the temperature using chemical freeze-out temperature normalized to 200 GeV. So that's the one that's set up to here. And but at a lower collision energy, you can see they're quickly sharp increase at the lower energies. Okay, so this is a very typical check picture if you look at the next page. So in 2006, Chanai, Kaposta, and Larry McLaren, they published paper. They actually collect the eta over S for different material, for example, helium, water. You can see this characteristic shape, the check shape, at the minimum is reached at the transition point. They predicted, actually, in that case, that a nuclear matter should behave like this. There's no clear experimental evidence. I think what we find here, this is a clear experimental evidence to show that there is a transition happened. This is low energy and hydronic state, not these three, but this is 7.7 GeV hydronic dominant. So that shows clearly this is check shape. So to some extent, this measurement is a clear evidence that for nuclear matter kind of phase structure here, and quark-gluon plasma state and also hydronic state looks like that. I think it is actually very interesting to observe that. Now come back to the V2 measurement. As I said, in a fixed target mode, we actually have a very good measurement at 3 GeV. So this is a recent publication by STAR called the disappearance of platonic collectivity. What we find is at 3 GeV, V2 is negative. In addition, the scaling we observed in high energy disappeared. That's why we put the title disappearance of platonic collectivity. And if we integrate of this V2, we can see 3 GeV all becomes negative. This is mostly because of a shadowing of by the spectator. If you go to high energy, the V2 becomes a positive. In addition, we also find that 3 GeV V3 is also much larger comparing to higher energy collisions. So all this comparing to model calculation indicate at 3 GeV definitely is hydronic interaction dominant medium, and at high energy, especially above 7.7 GeV, perhaps is QGP dominant, more dominant state. So that is one clear indication. Now let me move on to critical behavior. To do critical point search, actually we needed, in 2008, we thought we needed a new observable. There was a INT workshop. So we had lots of discussions there, what observables are needed for critical point. We know in strong interactions, there are three basically conserved quantities: baryons, charge, and strangeness. They're conserved in strong interactions. So in order to search for the critical behavior in strong interaction, we're looking for the fluctuations of these quantities. We also know the higher the order of these correlations, more sensitive, but you have to pay the price because this high sensitivity also highly sensitive to background. So that's what we struggle all the time. In addition to these two advantages, these conserved quantities are also very good to connect to theory calculations. I will show you in a moment. Here, picture-wise, maybe not difficult for people first to hear this high moment. Picture-wise is first order just the mean. Second order sigma is just a variance of a distribution. The third one is difficult to imagine, but you can see is how symmetry, it's called skewness, how asymmetry is distributed. If this one looks like a long tail on the positive side, on the right-hand side, and the other one is the negative. For the fourth order, this is called kurtosis, and it's how the distribution peaked. So it's called kurtosis. Actually, our analysis now is not limited to fourth. We already have up to eighth order, but today let's focus on only on sixth. On the fourth is enough. So the combination of these moments in experimental measure can be constructed by measurement of covenant ratios. For example, sigma squared over mean, it's just C2 over C1. Kurtosis times sigma squared is just C4 over C2. And these ratios is exactly corresponding to the ratios of susceptibilities from theoretical calculations. Could be from lattice, could be from thermal model calculations. So to a large extent, the volume part is cancelled out. So this comparison can be made directly with between experiment and the experiment and theory calculations. That's I think it's a very important feature for such for this observable. I'll give you one example also later in this talk. For high moment, what is a theory guidance? Actually, we do not really, even today, much guidance. But here we have a very good paper by Misha Stefanov. He says, if you have a critical point here in the phase diagram, and if the freeze-out curve is along this way, so one would experience, you will never hit the critical point per se, right? But you may hit by the scaling region. I call that a critical region. So when you get in and get out of the region, you may see some pattern. So Misha speculated that for fourth order, we should see the baseline and then show a dip, then show the peak. Peak, my understanding is where you approximately very close to the critical point, then coming back to the baseline. So you're looking for this oscillation pattern. So that's what we are looking for, indication of a critical region. So that's experimentally what we do. So how do we do that? So first we have to measure the centrality of the collisions. So this is a measurement of charge particle distributions from 7.7 GeV all the way to 200 GeV. And you can see that they are different within same acceptance, but their distributions are dramatically different. For higher energy collisions, multiplicity is much higher. This shaded blue region is the top 5% central collisions. And we use this data trying to looking for critical point because we believe, we know that in central collisions, they are more sensitive for the critical behavior. Before we go to final physics conclusions, we actually, after the collision centrality, we have to do efficiency corrections. We have to do uncertainty estimation, and also we also have the pileup. We have to do the corrections. This is especially severe for the fixed target experiment. So many correction steps we have to do, and we have to do very carefully check these corrections. For those who are interested, I suggest you start with these references. You may understand a bit better. Then if you have questions, you can send the messages to me or to us so we can discuss. later. So then now this is the beginning of the final result. This is net proton distributions from different collisions, all the way from 7.7 GeV to 200 GeV. Those are raw distributions, no corrections here. And only for top 5% central collisions. As you can see, for 7.7 GeV, the low energy, the net baryon density is high. Therefore, that the distribution is a positive, the large value, but the width is very broad. On the other hand, for 200 GeV, it's close to zero. Zero meaning your particle production is fairly dominant. Negative, positive are same, but here clearly is not, because we know there's a 10% chemical potential here. So from this raw distribution, we can extract the skewness and kurtosis. So there we can look at the physics. As you can see here, let's focus on kurtosis. For high energy, it's relatively flat, but at the 19 GeV, immediately you see a dip. Then when you go to lower energy, it comes up again. So this is our 2021 published PIL paper. This clearly shows that some dip and some rises here for central collisions. On the other hand, for peripheral collisions, 7 to 80% open square is a flat, nothing happens. That's actually is a very interesting, important result. From this measurement, we speculated something's happening. That's why RHIC started the second B-managed scan, because in B-managed scan 1, this data point, you can see the uncertainty is really large. We projected from B-managed scan 2, we expect to reduce statistical uncertainty to this green band. In addition, you can see this yellow band here. This is a URQMD, this transport model calculations. It is basically continuous decrease, and we understand this decrease is because in the fixed acceptance region, when you decrease the collision energy, you put more and more baryons into this region. Therefore, due to baryon number conservation, you suppress these correlations. That's why more and more deviate from this. And I should have mentioned, when I said the model expectations, we have a baseline. This baseline not necessarily flat. We need a dynamical baseline. So I think after this paper, we realize, so this perhaps is I call a canonical line. This is the future baseline for such analysis. And when we published this paper, we did not have fixed target data. This is blue arrow, is a star fixed target data covered regions. From that paper, we actually did some statistics analysis. For the fourth order, we find there's a 3 sigma effect deviated from this straight line, the ground canonical limit. So that means this data is consistent at 3 sigma level with a non-monotonic energy dependent, as the theory model suggests this non-monotonic behavior. So soon after we published this paper in 21, we also completed analysis at 3 GeV. This is shown here. I'm not going to go to detail here. And this is experimental data with large systematic uncertainty. Statistically, actually, it's very small. We have very good statistics. This large is complicated because the fixed target experiment. I think in the future we should reduce this. We'll reduce this dramatically. And at this energy, you can see the URQMD calculation, which is this brown cross here. It's consistent with this very, very clearly. So you can see at a high energy transport model, at least URQMD cannot fit very well below 39 GeV. Actually, you see they deviate except this point. But at 3 GeV, it's very much consistent with data. Do you remember, as I mentioned, about the collectivity at 3 GeV transport model also can reproduce this. So this means at 3 GeV or lower energies or higher baryon density region, hadronic interaction dominant. So if you want to search for a critical point, you need to search, must be above 3 GeV. So that's a conclusion of 2022 paper, this paper. So if there's a critical point, should be between 3 GeV and 20 GeV. So that is the region covered B- scan 2 supposed to do. So that is actually very, I think it's a very crucial point for the whole this game of search for critical point. Now let me make two notes to you, and I think it's interesting point I'd like to discuss. One is in the meantime, we also analyze the data of 200 GeV proton collisions. So this is the result, and you can see blue crosses here for C4 over C2, and for C5 over C1, and C6 over C2. This is a bigger cross, is the averaged multiplicity average. So this is as function of multiplicity. We know lattice calculation, for example, C6 over C2, predicted that it's negative C6 over C2 if QGP matter is formed, and for smooth crossover. And gold-on-gold collision result clearly show this trend, indicate in the central gold-on-gold collision is QGP matter. But interestingly, in PP collisions at the high multiplicity end, I'm not saying that's the case now because that the error bar is still large here. It shows that it's very rapidly pointing to the negative region, indicate that there may be formation of QGP in high multiplicity proton-proton collisions. So this data shows, because the slope is different, showing here, I argue that the PP collisions are actually more efficient in producing QGP matter. So either at RHIC 200 GeV collisions or future at least PP collisions should be very important to analyze this data, so that will help us to understand this behavior. So as I said earlier, that this comparison with lattice, the high moment with the theory calculations actually is very good. And this is the first time I think the real heavy ion data compare with the first principle theory calculations. The others are model comparisons. So here is the first principle calculations. So I think it's very important. The second point I would like to mention is I said, since we can compare with theoretical calculations, we just did a small exercises with people, and this is mostly done by the Bashish. So we compare this star published result from 200 GeV all the way to 7.7 GeV. What we concluded from this high moment measurement is down to 39 GeV, systems are consistent with ground canonical. Down to here, you see, it's very consistent. Below, actually, the deviation starts, becomes dramatically. There are two possibilities here. One is the system is not ground canonical. Maybe we should try to use a canonical to describe in a low energy or high baryon density region. Another point is maybe we are entering the critical region. Therefore, the system becomes violent and not consistent with equilibrium anymore. So this remains to be tested. I think it's important that we should test this region, canonical analysis and the critical point search. So these two, yeah, I promised to show you. So now hypernuclei production. What is hypernuclei? I hope you know. If you replace one nucleon in a nucleus, inside a nucleus, and this becomes hypernuclei. Why hypernuclei is important? You know, now it's very fashionable that about a gravitational wave and neutron star merging. Neutron star has certain properties. For example, its mass less than 2 solar mass and the radius is between 10 to 13 kilometers. And in the calculations, the very important ingredient is nucleon baryon interactions, not nucleon. Nucleon, hyperon nucleon, and perhaps hyperon nucleon, and hyperon. We know that if we use only two body interactions, this is too soft. If it's only hyperon nucleon interactions, it becomes too hard. So now people say we maybe need a combination of a 2-body plus 3-body interactions. But the basic parameter of hyperon nucleon interactions, actually, we do not know. So our interactions may help to do that, to extract those parameters. I think start with 3GeV gold collisions already published 2 PRLs related to hypernuclei production. One is a DNDY of hypernuclei, and this is to me very important. It's the first such measurement. The second one is already accepted by physics review letters. It's a collectivity measurement, V2 of hypertriton and hyperhydrogen 4. You can see they follow similar trend of lighter nuclei in terms of as function of particle mass. This, I argue, is only the first step. It's a beginning for us to understand the hyperon nucleon and even later hyperon interactions, because this is data only from 260 million events. We have 2 billion events to do that. So more will come in the future. So this is a model calculation long time ago. Actually, it's almost 10 years ago. They already predicted there should be peaking of hypernuclei production. So I think it's very important that we explore in this region. So this is also my motivation to future direction. Let's say CBM experiment after fair. Now, this is the interaction rates as function of collision, energy. Star is showing here. This is B- scan 2. I highlight in yellow, and the star collision rate typically is 2K in heavy ion collisions. To this extent, the S-Phoenix, which will take data soon, is about 15 kilohertz, and ALICE in the future, ALICE 3 will be above 100 kilohertz. So that is collision rate for collider mode. On the other hand, the CBM is designed to take this up to 10 megahertz. So this is really the high density, high luminosity frontier, and CBM will operate around will be close to 800 MeV. So this, if you want to do precision measurement, especially for hypernuclei and other exotics, this is a place you want to do the physics. Of course, if you want to study in details QGP properties, you should go to the ALICE to study over there. So this is a CBM experiment. The energy range for first phase is of 2.4 to 4.9. And it has high intensity and the collision rates up to 10 megahertz. Supposed to operate in 2018. So this is the beam come from 618, then go to 600, then come to CBM cave. So that's a plan. And this is the detector, target, and silicon trackers are inside the dipole magnet. After that is RHIC detector, TID, and time of flight for particle identification. Then it's a calorimeter at the very end. The major physics program is dileptons, both electrons and muons in CBM, and higher order correlations, including this high order Coumadin measurement, looking for critical points. and flavor productions, including both S-quark and charm and hypernuclei production. So if I summarize here is, I think we have a fair amount of knowledge for μB close to 0, and that's a future LHC program. Now, if we want to get information for critical point, phase boundary, and nuclear matter, equation of state at the high baryon density region and hypernuclei production, we need to go to continuous star beam and scan 2 data analysis and the CBM experiment in this region. I think there's a lot more to offer in the future. So at the end, I would like to thank those people. We have a constantly discussion day and night. And also I'd like to thank the Humboldt Foundation for their support. Thank you for your attention.
Thanks a lot, New. The floor is open for questions, so you can raise your hands or just type your question in the box.
I cannot see any, so.
Yeah. Okay, so there is a hand. Go ahead.
Hello. Hi, Nud. Thank you for a really interesting talk. I have a question about your slide 29 when you show lattice results.
Slide 29.
Mm-hmm.
Yes.
So I am just wondering, because of course you can calculate lattice results at different temperatures. So at what temperature range, what temperature do you use to compare to experiment, and how do you establish that that's the correct one?
This is, here we took TC.
I see. So exactly at the critical point.
Yes,
okay.
Yes, yes.
I mean, transition, not the critical point, sorry, at the crossover.
Yes, this is only for crossover.
I see. Thank you.
This is Agnieszka, okay.
Yeah, sorry, I should have said.
I did not recognize you earlier, so okay. Yes,
yeah.
Thank you. Yeah.
Any other questions? Maybe there'll be some more questions, but I had one meanwhile. So on slide 26,
Yes.
Yeah, so for the 70 to 80%, the points that you have, are the error bars significantly smaller than the 0 to 5%?
Yes, they are. The error bars are smaller. Yes, this is because for the high order, for high order culminant, the error bars actually proportional to its sigma, second order, and sigma is proportional to its multiplicity.
Yes,
the higher multiplicity, the error bar is larger, and for more central collisions is more difficult. In other words, is for example, LHC is also much more difficult. You compete statistically. Yes, it is. Yes.
And so this includes both statistical and systematic.
Yes. Yes.
Okay.
Yeah. Good observation. Yes, it is.
Okay.
Yes.
Okay,
we spend years on that. So.
Yes. Okay. I also had one more question. This might be a very naive question. So you mentioned the EPD helped in getting the flow, the event plane measurement better. Can you say a few words about how? Because it seems to be a more forward detector, right?
It is more forward. It's also much bigger, and it's much bigger, kind of covered wide pseudo rapidity range, and a much better granularity. It's especially designed for such measurement. And before that, we use a BBC. BBC is we call the beam counter. The granularity wise is much coarse. Therefore, this detector is much, much better. Yes.
Okay.
Right.
Thanks.
Yeah. At least, increased, 20 to 40% in terms of event plan determination. Yes.
Okay, I mean, this determination happens more at the forward rapidities, and then I guess that helps you determine the plane for the entire rapidity range.
Yes, it's covered the wider pseudo rapidity region, and also further away from TPC help us to suppress autocorrelation as well. Yes.
Okay. Thanks. So Tribhuvan has a question. Go ahead.
Hello, I have the question on the plot where C4 by C2 is plotted as a function of energy, and on top of that URQMD baseline prediction.
Okay.
So that you have that URQMD prediction is basically deviating from one or the Poisson baseline. So
yes.
that you have argued it as due to more baryon is getting stopped in the accepted rapidity coverage. Okay. So I am not able to connect how depositing more baryon will affect the higher order cumulants.
It affects all order, not only high order. I just give you one example. If we have a detector, we collect all the baryons. Just imagine. The correlation should be 0, right?
Yes.
That's it. We are somewhere between 0 and all. And what happens in this calculation, also in data, our plus minus half unit of rapidity is fixed. The detector acceptance is fixed. Yeah. Therefore, low energy because stopping power, you put more nucleons in protons in this case.
So what will happen if one will vary the centrality cut energy-wise? One can vary the centrality cut so that one can capture exact number of baryon in all energies.
You vary the centrality to keep the same number of baryon, what they are looking for. I would try to go to as central as possible in order to generate matter and perhaps also think maybe create the critical behavior. That's our motivation. But by fixed baryon number, what do you learn from that?
No, so you said due to more baryon, there is more fluctuation. Okay, as we go to lower energies in the
no, it's not a more fluctuation, it's a suppressed. The correlation is suppressed. You can see here. Can you see? Yes, because the more baryons are contained inside our acceptance. So the suppression the correlation is suppressed.
Okay.
Yeah.
Thank you.
So Ashwini has a question. Go ahead.
Hello, no, such a nice presentation. So if you go to the slide number 29, where you are showing the cumulant ratios with different collagen systems, so we can see that the result with isobar agrees with that of the gold. So what is the motivation of doing the analysis in different systems? It is just to see the system size dependence, because we should not expect that this should affected by changing the collagen system, because after it is a study of the QGP. And also we are seeing that the result at isobar agrees with that of gold. This is my naive expectation. Is there any more motivation that we are start doing this measurement at different collagen system?
Yeah.
What is the basic motivation?
Yeah, thank you for the question. So originally, this plot was done with proton-proton collisions plus gold-on-gold with these red triangles. So we observe this behavior. Actually, the paper is just released to the collaboration for review. And then we noticed we have for isobar collisions, we have for each collision, we have 2 billion events. Gold on gold, we actually have less than 1 billion events. That's why error bar is large. So we expected to see more detailed behavior. So that's why we decided to analyze that, to see if we have better behavior. But you can see, at least at the moment, the preliminary result doesn't show. We are struggling with this data at the moment now. Yeah, it's purely because high statistics. So we wanted to analyze this. Yes, because our gold on gold statistics is not very good in the high multiplicity regions.
And one a very naive question. So why we are comparing all this result with URKMD, because it is just a transport model and there is no concept of QGP there. So why we are studying the property of QGP using this transport model?
First, it's because you need a reference. We know there's no QGP, and we need a reference. And without QGP or phase transition, actually it's good. It's just like plain reference for that. And on the other hand, you see, we also show here, I did not mention a lot, this long dashed line is a ground canonical behave. So in a system, if you reach the ground canonical, you don't need QGP. Any system, this kurtosis should behave like that. So that we know it should behave like that. So therefore, it's okay if it's in the high multiplicity region, if it's just purely statistical behavior. So it doesn't matter what physics you have there. So in that sense, URKMD is very helpful. This is one. On the other hand, in the low energy, for example, at the baryon stopping region at 3 GeV, URKMD behave reasonable, not perfect, many issues with that, but behave reasonably. Yeah.
Thank you.
Yeah, that's why we use. We don't have a model which has a QGP, has a purely hadronic interactions, has a mean field, and we do not have such model yet.
So Kaiser had a question. So he's written it down. Can you say something about the absence of NCQ scaling at LHC?
Can you repeat?
So can you say something about the absence of NCQ scaling at LHC?
I don't know. I know the observation, but I do not know. Yeah, we should ask a series.
That's an interesting question. Yeah. Okay, so